Okay, next up is cell theory. The cell theory has three main points or three main facts. Number one, all living things are made up of cells. Number two, all cells come from pre-existing cells. And number three, the cell is the basic unit of life. So now down here to the question. In 1838, Matthias Schleiden determined that all plants are composed of cells. All plants are composed of cells. In 1839, anatomist Theodor Schwann proposed that all animals are composed of cells. In 1855, biologist Rudolf Virchow added to Schleiden and Schwann's observations and proposed that all living things are composed of cells. Okay, we already mentioned that up there. Which statement is also part of Virchow's cell theory? So let's see, all cells have a cell wall. First of all, that's not one of those three things we pointed out there, and cell walls are only in plants. So they're not going to be in animals. So that's not going to be our answer. Letter G, all cells arise from pre-existing cells. That is in our statements up there, so that might be a good answer. Let's go ahead and hold on to that one. H, all cells are capable of photosynthesis. Nope, that's only in plants. And all cells can develop into any other type of cell. And no, that is not one of our statements. So the best answer here is going to be G. Okay, let's jump on this organelles. First of all, organelles are parts. That's the parts of the cell. They're the parts of the cell with a specific function or job and structure. Down here, we're going to go through some of the more common or well-known organelles in the cell, the ones that you guys learned in the 7th grade. First off, we've got our nucleus. The nucleus is in the center of the cell. It is the control center, and it's where the DNA is stored. The mitochondria, here it looks kind of bean-shaped, and it's got these little squigglies in it. It is where the energy comes from. It's where they convert the food to energy, and it's often called the powerhouse of the cell. I like to say it's the mighty mitochondria, kind of like Mighty Mouse. The cell walls are found only in plants. They're squares. They surround the cell membrane and the rest of the cell, and they're really there for mainly support. That's why the plant cells are square and not ovals or kind of rounded like the animal cells and the other cells. Then we've got chloroplasts. Chloroplasts are also in plants only. They are circular. They've got these little rings inside them. Sometimes people like to refer to them as the pancakes. That's where the chlorophyll is, and this is the organelle that uses the sun. It collects the sun, and it uses it along with sugar to make energy, make food, glucose, and ATP. And then we've got the vacuole over here. Vacuole in plants, it's easy to spot. It's the largest sac. It's the largest organelle in the plant cell. In animal cells, it's a much smaller sac, but for both of them, it is used for storage. The diagram of a plant cell is shown below. Here we have the plant cell, that large vacuole. The large vacuole we can see in the plant cell, and then of course we see this oval with the sacs like we referred before. That is going to be your chloroplast. We can see the stacked pancakes in there, and then this would be our nucleus. And let's see what the question is asking us. The question says a function of the plant cell structure shown in the enlargement. Okay, so we're looking at this large. We know that the stacked pancakes is the chloroplast. Provides support. Nope, that's going to be the cell wall. Direct all the cell's activities. That's the nucleus. Uses energy from the sun to make sugar. Yes, that's exactly what the chloroplast does. And then regulates substances that enter and exit. No, that is the cell membrane. So our best answer is C. Second question. Plants use energy from sunlight, water, and carbon dioxide backside to produce sugar, which structure is found only in plant cells. Okay, we reviewed those earlier, and helps plants capture energy from the sun. Well, only in plant cells, it's either going to be the cell wall or it's going to be the chloroplast. And the chloroplasts are responsible for capturing sunlight from energy, so that is going to be our best answer.
All right, guys, now we're doing weather. So weather revolves all around convection current. So cold air, it sinks because it's very dense. It's also very dry. There's not a lot of moisture. Think about in the winter, that's when we, have chapped lips and dry skin a lot more. High pressure, because it is so dense, so everything is basically pushed down, including the clouds. So it's usually very clear skies. We see an H, and we say that is happy weather. All right, basically opposite that is going to be the warm air or particles, fluid, because this could be both air, it could be water, and it also occurs in the mantle. So warm air rises, just like your shower. If you take a warm shower, it holds a lot of moisture. The warmer it is, the more fog you have raining down your mirror when you get out. It is a low pressure. That means it's rising. It's not pushing down a lot. So if everything's rising, it usually creates clouds in the sky. Okay, and all those with all that moisture, and so that typically is associated with lousy weather. You've got kind of cloudy, overcast skies. It could, possibly rain depending on how much moisture is actually in there. All right, oceans also drive weather, especially around coastal cities. So if you have a warm ocean current like we do here in the Gulf of Mexico, that extends all the way to Florida. And at the East Coast, really, and that holds a lot of humidity, and you have the majority of your storms there. That is the #1 ingredient for a hurricane is warm ocean water. In fact, you need at least 80 degrees or more in order for it to even have the potential of being a hurricane. And hurricanes all are on that side of all start on the East Coast. Really, California on the West Coast, they don't have hurricanes because what they have is a cold ocean current coming down from the poles, and that what that does is, just like before, cold air is very dry, or it cools the air above it, cools the ocean air above it, which is dry, and so if you've ever been to California, it's very dry and very low humidity, very cool air, beautiful clear skies. That also has to do with their wildfires. Their air is dry, therefore any little spark can set off major wildfires. All right, so the question says, what is one condition that is necessary for a hurricane to form? All right, again, what we talked about before is that you need to have at least 80 degrees or more water. The water temperature needs to be 80 degrees or more, and so that would be consistent with warm ocean water. A strong cold front right here is going to stop a hurricane. Stops it. And cold ocean water, again, would stop it. And a strong warm front, that might increase it, that might intensify it, because it is it's going to bring in more humidity, which is going to necessary. But what is necessary for it to form is going to be warm ocean water. All right, so hurricanes and similar storm systems begin over oceans. The map below shows average surface temperatures at the oceans in the summer. So just by looking at this key, we can see that this is -9 to 12 degrees Celsius, and then just by looking at the 12 and 26, this is going to be our coldest. This is going to be our warmest down here, this one's kind of in the medium with, in the middle with kind of medium dry weather. Okay, or ocean temperatures. So we know that at least it needs to be 80 degrees. The warmer it is, the more moisture it holds. So we're looking for this light colored one, which is going to be number 3. Now that does make sense because that's right here. That's the equator. So that's where most of our hurricanes are get affected, or at least start, and then they can move, up or down from there. But because we need at least 80 degrees or more in order to have that, so that's going to be right around the equator. So that is going to be area 3. Okay, so what is the formula for finding density? Well, if we look on our formula chart, we can find that it is mass divided by volume. Now, density is how much matter something has in it. So, something that is very dense is going to be heavy. Something that is not very dense is going to be light. So, typically. So, mass divided by volume. We put this into the triangle. Again, remember everything to the right of the triangle has to stay the same. So, mass needs to be on top of volume. So, the only place that mass can be on top of volume is if we put mass here at the top. It is still on top of volume, and so I'm just going to put the D for density over here. So what we do here is we make our triangle, and we can use this triangle to determine whether we're solving for density, mass, or volume. So the student calculates the densities of the unknown substances and compares them with the table of densities of known substances shown below. So if I do this, we're solving for density, so it's going to be mass divided by volume on all of these. So 6.95 divided by 4 is 1.74. The next one is going to be 2.27. 5.4 divided by 3 is 1.8. And 10.35 divided by 5 is 2.07. So here are the densities of some known substance. The question below says, which unknown substance is most likely carbon? So carbon right here is 2.27, and so I come up here, it's not going to be this one. That looks like that might be magnesium, okay, Mg for magnesium. 2.27, that looks like that's going to be carbon. 1.8, that's going to be phosphorus. That's P for phosphorus, and then 2.07, that's going to be S for sulfur. So my answer is going to be number 2, substance 2, which is going to be B. So the answer to this one is going to be substance 2.
Okay, how are we going to read a graph? Anytime you have a graph, the first thing you want to do is check out the X and Y axis. This is distance versus time. This is the exact same activity that we did with the motion detectors. So you remember we held the whiteboards when we had the starting position. When we walked forward, remember what the graph did versus walking backwards, and then when we sped up. So the graph here, so whenever you have a line that is a straight line, but it is going up, then you are walking away from the start. Right here. And it's not a very steep slope, so it is slow. As it speeds up, you're still walking away, but when it's steeper, so you're still walking away. But faster. Right here, in this section right here, you are not going any distance, so you have stopped. A flat line, when it's completely flat, means that you have stopped going forward, so you're not moving. And then, of course, as you go down a downward angled line, it's going to be moving back towards the start. Back to start. So the slope gives the speed of object. Steep is fast.